This is the CDFam podcast, with recordings from the CDFam Computational Design Symposium held in Amsterdam in July 2025. The following presentation is from Mathias Fuchs from McNeel on Rhino, Grasshopper II and TRfem, on computing heat flow inside solids natively inside Rhino. It's a very visual presentation, more of a demo, so you may want to jump over to YouTube to get the most out of this one.
It's my pleasure to introduce Philipp Schneider from Conversely, and my name is Mathias. I'm from McNeel, and we have the pleasure to demonstrate some thermal analysis of a very cool printed project, and Philipp is going to introduce this.
Thanks a lot. So before Mathias goes into the wonderful, crazy stuff that goes on inside Grasshopper II, I'll quickly show the use case that he'll demonstrate it on. And I'll dive into, or quick deviation into architecture. You see a conventional wall detail. What if you combine this with a novel method for additive manufacturing of concrete in a powder bed at large scale? This method is a video called selective paste intrusion. We're based in South Tyrol, Italy. We have 15 cubic meters of available space. This is the secret sauce that we're cooking with, which is not so secret because it's cement. And we're injecting it into a particle bed of dry powder. And here you can see some of the wall elements that we'll be showing later. Exactly. And what does this allow us to do? Well, it allows us to build in a different way. Here we're using spherine as the infill of wall elements that we're printing in one piece to combine load-bearing capacity to bring down the compressive strength inside the bound volume. And inside, the clue is that we trap the particles. So highly porous, low density, and low thermal conductivity inside the bound cement to produce wall elements in one go and then assemble them on site. This has been a trade fair booth that we've been doing as a kind of test for this method where the infill is actually shown. And we're going to apply this at a different scale now where we're going to build a small office structure at our facility with only 3D printed walls with spherine as the infill structure. And Mathias will show how on earth we actually simulate this because we need it cheap, we need it fast. And this is where, let me quickly switch, Grasshopper II comes in, I hope I don't mess anything up. And this is just one segment of this larger wall where you can see the outer shell, the inner shell, and the spherine interior structure. And you have to think about in the void here being loose particles of low thermal conductivity aggregates. And Mathias will continue to show the crazy stuff he's been working on.
Thanks, Philipp. All right, so yeah, the task is we are being given this really nice geometry here. We can just see the concrete and the rest is loose gravel insulation. And yeah, so you might know Ladybug, you might know a lot of thermal analysis, but this is a 3D problem, okay? So let me give away the main result that I do want to drive home, and namely, these are the thermal isosurfaces here. I'm not very much a fan of slicing. I think that our brain likes transparency much more for displaying actual volumetric analysis. And due to some GPU thing that we have no influence on, the order, there's some very slight flickering, but I think you get a very good impression of what the thermal isosurfaces here are doing. All right, so how does all of this, A, how is all of this done? And B, how does it fit into the overall philosophy of Grasshopper II, where you have fields as first-class citizens. So, of course, the temperatures here are a field, but that's not the only field that's in play here. Of course, the geometry itself is made from the isosurface of the SDF, the signed distance field of the central surface here. So let me demonstrate, for example, how the basic geometric process of thickening would be done. We would have, so let me increase the transparency of these ones here. We would, for example, in Grasshopper 2 just have this mesh that we have referenced. You have a distance field, you have a fall off, and then you have the isocurves. For some reason, I have to bake them here right now due to some display glitch, but you can still see what's going on. So yeah, this is already very nice because the field itself is not voxelized. The field itself here that we are talking about is just, if you like programming, then it would be a closure object. It's just something that has a promise to be evaluated at later times whenever you like. So it's just something that you can evaluate at X, Y, Z. It's a present that says, evaluate me at X, Y, Z. And this concept has existed in Grasshopper 1 already, but was not very well known. And in Grasshopper 2, it is a full first-class citizen. So you can see it's just a display setting here that doesn't allow me to preview those isocurves, but you see that they do update here with a fall-off function of the distance field. So this is how this geometry is processed. And let me now try to explain how we use this concept to arrive at the actual thermal analysis. So there is, first of all, yeah, we can generate a structured grid. Right? So one thing you can do, or one thing we are doing, is we just take a mesh and we interpret the 4 indices of the mesh face as tetrahedral corners. And this gives you the notion of a truly volumetric entity in Rhino for free. All right? So this works without any plugin. You just can take this and interpret it as a tetrahedral mesh, and that's what we're doing here. And that's what TRfem, this plugin we're talking about, operates on. So apply, for instance, these transformations here. So you have twists in Grasshopper, and you could, for instance, perfectly well just bend such a mesh around an axis with an angle 1 and an angle 2. And you would sorry. So you can just interpret these meshes as Rhino meshes, and then the all usual Rhino operations continue to work. So you can delete faces, you can edit all these. You have all of these mesh editing functions here at your disposal. When we now try to make this such a mesh available for an actual finite element analysis, then we need this tetrahedral mesh for the thermal analysis. We just plug it into a solver component which just takes such a mesh, interpreted as a tetrahedral mesh. It takes the material conductivities, and it gives you the temperatures, which we can then plug into a usual marching cubes or isosurface component. This is done in such a way that you don't need to wait overnight for a finite element analysis like this. This can be done in real time. So for example, let me try to see what happens when we modify the material properties here. So for example, you might be interested in trying to optimize the infill material here of this gravel in this case. Engineering. So I really want to make clear that this is, on the one hand, geometrically very nice and obviously a very powerful concept to play with, in particular since these isosurfaces that you see here are not at all NURB surfaces, right? There's no way to generate these smoothly interpolating isosurfaces other than through this mechanism, basically. But I want to make clear that this has an actual impact on the engineering aspect here. So you might know the whole story about the U value, about insulation, about all the practical problems in construction. And here, we actually do get the power loss of the structure in watt per Kelvin. So you can directly convert that to money if you want, right? So the per Kelvin means the temperature difference between inside and outside, and watt is basically euro per hour or something, right? So this has direct impact on the efficiency and on how you can sell your geometry to the customers. So, for instance, you want to optimize the thermal design here, and what we can do is we can parametrically update the conductivities of these materials. Let me show you how this is done. So this also serves as a kind of reality check. If both materials are just the same and have just the same conductivity measured in watt per meter Kelvin, then the isosurfaces are just parallel to the XY plane, right? Because then there is no thermal information, and the more we let this ratio of the two materials tend to, well, let's tend them to something a bit more drastical, 5,000. So for the sake of this argument, then we can see how in the limit approach the case where one material just acts as a perfectly adiabatic insulator. So in this case, it converges, yeah, well, there's a certain limit here until which we can apply it, but the more we act the slider, the more we will converge towards the case where the isosurfaces meet the boundary just perpendicularly. So by Joseph Fourier's law on heat transfer, on the adiabatic boundary, the gradient of the temperature needs to be parallel to the tangent plane at the boundary, because it cannot leak heat through the boundary. And this is the limit case that we can observe here, for instance. Or just for playing, we can also hypothetically try out what would happen if the situation was reversed and the concrete infill here was actually just a vacuum. And then the rules of these two materials here would be reversed. And let's try to modify in the other direction. Okay, well, so there's a certain limit until which we can drive this. But yeah, you can perfectly well simulate what would happen if you introduced more insulation material here, wherever. And I want to point out, all of this is just done including the meshing step, just obviously live here. I mean, obviously I can't do all of this in the live demo, but it works. It obviously works interactively. All right, so I do want to say something about the meshing aspect here, because you might know that tetrahedral meshes have this kind of very bad reputation, right? The tetrahedral mesh, oh my goodness. But it is not without reason that they are the industry standard for more than half a century in all kinds of finite element analysis. So, of course, you can say, oh, there's a boundary element method here, and you can avoid the tetrahedral meshing, and that's cool in the future and everything. Okay, fine, but then how do you do the structural analysis? All right, so there is a very good point to be made that tetrahedral meshes in 2025 should no more be something to be scared of. Now, a computer can only be a Mac or Windows, but not both at the same time. So due to MFC problems, TRmesh, the actual mesher, only works on Windows, but I chose to use the Mac for the presentation, on which it is faster. But for the actual meshing, I recommend you check out the TRmesh plugin, which gives you a very nice Windows GUI for the actual hard tetrahedral meshing problems. And what I'm doing here, well, I could just have imported such a mesh as a 3DM file, but that would have been a little boring. So what I'm doing here is just I'm modeling myself through without an actual mesher. I'm just doing structured meshes, right? So this box mesh is obviously just a structured mesh. And if you know the finite element analysis aspects here, then you can say, oh, it's just a structured mesh, it's just a lattice. Well, then it's just a finite difference method. Well, yeah, sure, then you would be right? But that's not the point here. The point is that the actual mesh here is just used as a demonstration for the capabilities of a general, very general thermal solver in Grasshopper. Yeah, to conclude this, I do want to make one practical point clear, and this is the materials. So you somehow have your mesh, you have a tetrahedral mesh, and each single tetrahedron needs to be in one material, either in the infill or in the gravel or in the concrete, and it needs to be associated with one thermal conductivity value. How is this done in a way such that you don't get too much headaches about doing this? Well, if you use TRmesh on the Windows interface, then you will get your materials directly from the Rhino materials. So there's a very seamless workflow that's documented on YouTube, and I'll put more documentation on the website over the weekend. Please read it, and you will see that it's very easy to just get the Rhino materials from the layers right into this TRmesh. So this is a very seamless workflow. And here, what I'm doing right here, if I can find the component, it's somewhere. Apply containment material. Okay, so this is the component here that will take a mesh, such a TRfem or TRmesh, tetrahedral mesh, and it will take a mesh that encloses the volume we're talking about, and will just apply all these material indices. So this is also extremely painless. There's no fumbling around with any kind of large indices or very obscure VTK file formats. I mean, I love VTK file formats and so on, but I think this one is a little easier. Cool, thanks. Check it out and let me know what.
Again, you may want to search up CDFem on YouTube and find the Amsterdam playlist to get the most out of Mathias's presentation. To learn more about the CDFem Computational Design Symposium series, to see the archives of previous presentations, and to learn about future events, visit cdfam.com.